Hey guys, so today I'm going to talk a little bit about some of the properties of water that are important for biology. And so first we have to start at looking at the general structure of water. And so as I'm sure you know, water is composed of hydrogen and oxygen. The formula is H2O. If we look at this little doodle that I have here, this beautiful little model, this is my representation of a hydrogen, and this is my representation of an oxygen. You can see that the oxygen is a lot bigger than the hydrogen. Okay? And so the hydrogen is the smallest element that there is. It has a single proton. Its accompanying neutron for most parts is just one neutron, and then it's one electron. If that hydrogen loses its electron, it becomes basically just a proton, which is important later on down the line, which we'll talk about later. Oxygen is just the right size to have a high electronegativity. And what it means to be electronegative is that you attract the electrons of other elements towards you. Right? And so this little hydrogen gets bullied by this big oxygen. Right? This oxygen has a large enough nucleus to attract that little electron, and its electron cloud isn't too big to prevent this electron from engaging with its nucleus. So when a hydrogen and an oxygen get together, right, in an instance such as water, the electron from the hydrogen will spend more time with the oxygen than it will with the hydrogen. Okay? And so when you have this water molecule, which is this shape, right? You have the two hydrogens at the bottom, the oxygen at the top, in this triangular form here. The electrons will spend more time here than they do down here. And so it creates this kind of temporary negativity around the oxygen. Right? It has a pseudo-negative charge, whereas the hydrogens have a pseudo-positive charge. Now the electrons are moving all the time. And so when the electron is back down here, that charge goes away. So it's a very temporary thing. It's called a dipole moment, dipole. Right? So this individual water molecule will have a temporary negative by the oxygen and temporary positive spots by the hydrogen. It's constantly in flux. Right? And so when you put a bunch of waters together, the negative side of the oxygen will attract the positive side of other water molecules. Right? And these are called hydrogen bonds. Right? The positive nature of a hydrogen over here will attract the negative nature of the oxygen, and they'll temporarily be friends. And then that dipole moment will end, and they'll separate. And then they'll join up with another one, and then they'll separate. And they'll join up with another one, and they'll separate. Join up with another one, and they'll separate. Right? And so it is this flux of bonding between these hydrogen bonds in these water molecules that makes water liquid at room temperature. Because the bonds aren't solid enough to hold the water in a very specific shape. But they are strong enough to keep the water from flying away as gas. Now, if you lower the temperature down to freezing, which is 0 degrees Celsius, as you may know, right, the energy level of that water comes down enough that the hydrogen bonds are strong enough to hold the molecules in place. Okay? And so when the water molecules start getting stuck together, okay, they get stuck together in this crystalline shape. Okay? The bonds become secure and they hold in place, and then we get ice. Okay? Now ice has these gaps between molecules that liquid water does not. Okay? So ice is less dense than liquid water, which is very important for living things because that makes ice float. Okay? And if ice didn't float on top of the water, all of the living things that live in fresh water live in the ocean even, right, depending on the coldness, because salinity changes the freezing point a little bit. Right? But all those things would potentially not be able to live. Right? And considering that life started in water, the fact that life could persist in water regardless of temperature is very important for the development of life. Yeah? Some other properties that this hydrogen bonding leads to is cohesion. Right? And so water will stick to itself. Right? If you put two droplets of water close to each other, they become one droplet of water, right? And then they're stuck together. Okay? And that's just because the hydrogen bonds connect to each other, right? That makes sense. Okay? Similarly, right, there's a property called adhesion. And this is water sticking to other things that will engage in that dipole moment. So other substances that have these dipole moments will stick to water as well. Good example is glass. Right? So if you think of some water condensing on the side of your glass, it will stick there, right? It doesn't just fly off, it sticks. Okay? That's adhesion. And then the most complex property that this leads to is surface tension. So here in my model, I have a glass of water. Now, if you think about the very, 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 very top layer of water, okay? If we look at it and you think about it, that top layer, okay, has water below it, has water next to it, who it's friends with. Right? It's friends with that water. But it has no water above it. It's just air above it. Okay? And so it's not making those friendship connections above it. That means that the connections to the side of it and the connections below it are just a little bit stronger than the connections of the rest of the water throughout the entire glass, right? So anywhere else in the glass, there's friends above, there's friends below, there's friends to the sides, right? So they're sharing their connections. Okay. But the water at the very top, those connections are a little bit stronger, okay? And that creates surface tension. Okay? And so if you think about certain kinds of insects, they can stand on top of the water, right, if they distribute their weight across enough of the water. And that's solely because of surface tension. Right? There's enough bonding to create a platform for those insects to stand on. You can do it with paper. If you do it right, you can do it with a paper clip. But as soon as that surface tension is broken, like if you were to stab the water underneath that bug would fall through. Right, because you broke the surface tension. The only thing holding that bug up is the surface tension. And on the biological front, because this, is biology after all, some properties of water that are important for living things is the fact that it's a universal solvent. Right? A lot of stuff dissolves in water. Life started in water, right? So all of our chemical reactions are based on being aqueous. And that's why we require all the water inside of our body that we do. All of our chemical reactions are based on the fact that they're all dissolved in water. Okay? Because life started in water, we need water for our chemical reactions to work. Okay? Another important function is the regulation of heat in living systems. Right? It's easy to imagine in the concept of cooling. Right? If you get hot, you sweat a little bit, water evaporates, takes some of the heat away with it, and you feel cool. Okay. It also helps keep you warm. You wouldn't think of it so much, but water has a high rate of heat retention. It takes a lot of heat to change the temperature of water, right? And so that's why if you jump in the water, you'll get cold. Right? But that also means that it hangs on to the heat pretty well once it has it. Okay? And so by being aqueous-based, we can hang on to heat a little bit better. If you think about how hot and gross it feels when you're humid, you can kind of get a sense for that. Right? So it works in both directions. And lastly is the molecular transport within systems. Right? So our blood is mostly water-based. If you think about a tree, its xylem and its phloem, the movement of stuff throughout the tree is based on water. Right? And so our body systems require water to move stuff around. So yeah, that was an introduction to some water properties. Cool. Bye.